Now, floating back down to linear forces, it's worth recapping Newton's laws. He's got three regarding motion, but obviously Isaac Newton was busy doing all kinds of physics. The first one, an object at rest or moving at constant velocity will remain so unless acted upon by a resultant force. So, on the same slide, we've got Newton's second law. The resultant force on an object is equal to the product of its mass and acceleration. So, in other words, pardon me. In other words, F equals ma, everybody's favorite one to remember. Rearranged, the acceleration on an object that's experiencing a resultant force is that force divided by its inertial mass. Fab. So, for example, a satellite, there's only one force it experiences, downwards, therefore its acceleration is also downwards. Sorry, I've drawn that slightly slanted. Acceleration is also downwards, despite the fact that its velocity is constant horizontally. And indeed, that horizontal velocity, it will be constant as per Newton's first law until a resultant force acts horizontally upon it. Maybe it'll sort of collide with the atmosphere and there'll be friction, or maybe it'll fire its thrusters and that'll interfere as well. But until that day, it'll carry on happily at constant velocity. Fab. So you've got Newton's first and second laws both applying in the case of a satellite. The third law is a slightly more technical statement. Consider two objects, fictitious objects, A and B. If A exerts a force on B, then B exerts an equal and opposite force on A. When I was talking earlier in the exam technique session, I said that there are certain phrases the mark scheme loves. And whenever you're talking about Newton's third law, please mention equal and opposite in some combination, those two words, equal and opposite. The way we've written it here will exert a force of the same type of equal magnitude in the opposite direction of A. That's a lovely way of putting it. But even if you're in a rush, include the phrase equal and opposite, please. Right, so what's a good example of this? If, for whatever reason, my astronauts in the satellite chuck an apple out, there's an apple falling to Earth, we're fairly happy with the idea that it's going to accelerate pretty quickly towards good old planet Earth. However, what Newton's third law asserts is that whatever the weight of this apple is, that same force will also act on the Earth towards the apple. However, of course, the acceleration will be very different for the two. You can say, look, the weight on the apple is equal to the force on the Earth. But of course, by Newton's second law, that's equal to the mass of the Earth times whatever its acceleration due to this interaction is. And it's also going to be equal to the mass of the apple times whatever its acceleration is. But of course, the mass of the Earth is huge and the mass of the apple is comparatively tiny. And so by comparison, the acceleration of the apple is going to be huge and the acceleration of the Earth is going to be tiny. Barely noticeable, in fact, which is why we don't see, you wouldn't expect to observe the Earth sort of massively going out of its way to meet an apple. Another good example, collisions. We'll talk about those later in this session. In a collision, the same force acts on each object, even if object A looks bigger than this one, looks more massive than B. The same force will act on both of them. It's just that because they've got different masses, it'll change their accelerations inverse to their masses. Object B has smaller mass, so it's going to have a bigger acceleration going away from the collision generally. Okie dokie. Hopefully that's not too confusing. And hopefully that's all clear. Let's do a little exam question then. A space probe is traveling to Mars at a constant velocity. Upon approaching its destination, the probe ejects its fuel tank backwards. If you weren't already thinking Newton's third law or Newton's laws in general, they make it explicit here. Describe and explain are our command words. So state what happens and then tell us a little bit of physics that explains it. With reference to Newton's laws, how the probe's motion is affected by ejecting the fuel tank. Hopefully, there's only two marks question. I should point that out. So just 2 bullet points should do. What happens and why? Right. It says Newton's laws, but you should hopefully identify we've got 2 objects here. I dare say an object A and an object B. We've got the rocket and its fuel tanker. So it's Newton's third law we're talking about. First point, on ejection, by Newton's third law, the fuel tank exerts a force on the probe equal and opposite to the force that the probe exerts on the fuel tank. Great. You're essentially stating Newton's third law, but just applying it to this specific context. But that doesn't mean the other of Newton's 3 laws stops applying. By Newton's second law, the probe therefore accelerates forward as the engine is ejected at a rate proportional to the resultant force. Got 2 bodies. Way. That's the sort of before picture. And then afterwards, the rocket carries on and my fuel tanker is sadly shed into the ether, into space.